Very exciting start with the first two talks. Third one focuses on trusted and responsible AI frameworks that accelerate the adoption of AI, especially on high-risk operations. A super interesting topic. We will learn more from Patrick Saint-Amand, CEO and founder of Zetane Systems. So let's give him a good welcome.
Great to meet you. All right. Okay. Hi, everyone. So I'll be talking about trusted and responsible AI framework. So we've built that at our company. I'm the CTO of Zetane, and we really focus on high-risk operations. And the reason is that models are not that robust up to now. So there's real issues there. And when we meet clients that work in high-risk environment, high-stake, high-risk, then we need to really make sure that the models are ready. So we develop tools to achieve that goal. So just a quick summary of who we are. We're in since 2018. We saw many clients, and we are building basically those tools to address those needs. We have some patents and so on, and like our focus is really about high-stake, high-risk. And yeah, and what you'll see today is about computer vision. Those are the first integration that we did, and we're also working on tabular data because there's also high risk in those situations. So our mission is really to make AI safe. And for now, I would say, and what I'll be able to show a little bit more, it's not quite safe. So usually when we talk about safety of AI, we kind of think about Terminator and so on, but the reality is like it's a very simple model that hasn't been properly tested. So even Terminator was well tested, I think. So that's the story. We're part of a consortium, Ericsson, Pratt & Whitney, Thales, and we're building this to make sure that there's a gold standard for AI and trusted AI. That's our team, so maybe I won't stay too long here, but just to say that we're a dynamic team, startup style, and we've been working hard. Started in the basement, did a lot of coding, and now we actually have products, and it's going really well. Some of our partners along the way, so mostly, you can see there's a Canada leaf, Quebec leaf. So if you see an accent, that's the French one. So that's from the Quebec side. And we have a few clients, I'd say, and there's more. Rheinmetall, Thales, that's in defense. You have construction, a big company in Quebec and Canada. Security, which is basically when you scan your luggage, that's what it does. It's computer vision that's been integrated. And also plain science. This was more like tabular data. Aroko also really. Like this one was actually the black box in the plane. So we had to analyze this using deep learning models. All right, so that's the kind of industries we work for. So one of common trend here is that it's all the industries that already have a culture of testing, evaluation, and making sure that the products and what they deploy is safe. When I say safe, it's the lives of people or very big financial potential problems. So that's and I'd say quality assurance. If in the company there's already quality assurance, it's easy to understand why, because it's been done for so many years and it's very mature. The concept of quality assurance. So we're not talking about recommendation engine, and so on. We're really talking about making sure that this works in the industries where there is real potential risk. I mean, I think everyone probably saw those stats, and from what I know, it goes from 80 to 90, and everyone has an opinion. But I would say that it's probably a little bit worse than that from what I've seen. 85%, I mean, they don't say which one are high risk, so I would say for something to get to deployment, it's really not easy. Because people would have that experience, deploy the model, and then it failed. The operator said, "Why did it do that? You lose trust into the model, and then you kind of stop. The project falls internally at the company." So that we've seen that in many companies of people we talk to. So there are many problems. Basically, it's about bringing what is done in academia, bringing it to the industry. And there's lots of amazing papers coming out every week, pretty much every day. And, but the transition is not easy because the data sets are really clean. They're almost perfect. Everyone worked on them for the last, I guess, 20 years, sorry, 10 years. And those data sets are well known. You basically almost like create a model that fits with that type of data set. So which is not what you get in industry, where the the quantity of data is usually lacking, and the quality needs to be really like, we need to work with the customers so that the quality is there, so that the data is usable. And also, everything's a black box. People heard a lot about the black box. It's still a problem. One, for the people who will kind of sign on the projects, they always say like, okay, but so what is AI? I don't know what it is and what it does, and it's just numbers that comes out. So there's a need to know of what it is exactly. And also lack of understanding of the AI solution by all stakeholders, and I included data scientists in there, because not everyone has the same view of a project in AI in industry, and everyone needs to kind of come together for this to happen. There's always, I'd say, at least 5 people involved, plus all the surrounding people that will interact with the project. So, and maybe one of the main thing, we don't know if it's safe, reliable. Testing and evaluation, we don't even know the concepts yet. What will be testing and evaluation for AI models hasn't been developed, and they have a different texture. There's a probabilistic nature to it. So we need to be understanding this more. And there's no independent testing framework. And I'd say like, this number here is probably what people look for. Like a data scientist build a model, test the model, there's one number at the end, validation, accuracy, or whatever other metric. And there's a few numbers, and that's the number that a scientist wants to get. But that's not enough, clearly. You really need to know more. And if you're lucky, you'll get like some kind of, with more numbers, which is probably one number per class, but that's pretty much what you get. So we wanted to solve this, and so what we did is that we take a test set and we slowly degrade it. And it's always a process. So we take the test set and we degrade slowly the test set, and then we evaluate each of them separately. So then when we do this, we realize that there's always a failure, a place where there will be a failure for any type of perturbation or transformation. In this case, it's, I mean, I'm from Canada, so there's a lot of snow. So first time you kind of lose one light, 2 lights, and then it becomes a bunch of balls. So this is a state-of-the-art model, YOLO-X. It was state-of-the-art 3 months ago, maybe now I think it's YOLO V7. And you have the same thing for so many transformations, like noise, impulse noise. You kind of lose even the tracking. There's no more bounding box. And one very dramatic case, this was a state-of-the-art model, medical, basically a breast mammogram. It was supposed to detect cancer, whether it's cancerous or not, or normal, and normal tissue. And 89% was really good, for at least that's a state of the art. And then when you test this model, and this is just a sample, when you change the contrast just a little bit, you change the contrast of this image, and you go down to 33%, which is mostly random. So if I go back, like, you can barely see that there's a change. And probably the only change you see is me trying to adjust the image so that they fit together. So it's really difficult, and this happens, and visually you would never know. And this happens all over the place for all models. And so what we realized is the needs is you need a way to test the robustness, and also you need the transparency for all stakeholders. So for us, it's really keeping in mind, like, we want it to fit with responsible AI principles. I mean, there's many organizations building those principles. There's Department of Defense of the US. There's also what's happening here, AI Act, and this is kind of really important. It's an important conversation. Otherwise, it won't really work. So we built those 2 tools. The first one is really to dive into the model, see all the components of the model, everything and I'll show an example. And then the second one is based on the evaluation and testing of models. So I'll show, so this maybe I'll skip this, but in general, what we do is we train a model, and after when the model is trained, you test it. And that's pretty much what is done in data science. And what we do for model inspection, we jumped into the model. So we have a software, and then we open, basically, it's hard to see, but here you can see like all the nodes. This is a neural network. The data goes from left to right. So when we hear about deep learning, it's this. So it's a lot of operators. All those little boxes are operators. And inside of them, there's more or less inside, there's tensors, which are matrices, a bunch of numbers together. And that's all a neural network is. There's nothing else in there. It's just addition, multiplication, and tensors. And when I say tensors, it's like big matrices. So here what we say, we dive into the model, we really look at every component of the model, so we're able to see everything. And in this case, you're already noticing something that on the side, it's putting attention to the side. So this means that it's really focusing on that section, which is not a good place to look at, because there's not a lot of information about the image there. So the data flows there, and then this is the example. So there's ways to solve this. You can add padding, you add normalization. And this, when I said a tensor, this is a tensor. In this case, it's a three-dimensional object, series of matrices, all stacked together. And the model basically takes these stacks of data, and it modifies it until you get to this prediction, which is a dog or cat, which is basically two components in the vector. So this is machine learning. That's a deep learning model. So that's good. So now you can use this to debug your models, and also now I hope you understand what deep neural network is. And so now we'll go to Zethane Protector. What we do is we take a model, we take a test data set, and we process it. I think here I made a mistake. I think it's like maybe 80 or 100. So we add transformations every day so that we can really degrade the data set and figure out where are the weaknesses. So in this case, we take, like I said, we can create a report based on the model and the test data set. And then we choose different algorithms such as GradCam, so that we know the attention of the model, and we also choose all the transformations that will be applied to the set of images. And then when we launch the report, we get a full report with all the good old metrics, the numbers that we liked before. So just put like in pretty shiny style. But we also have the score for each component of your test set. Here there's 184 images. When it's red, it means it's misclassified. If it's green, it's well classified. You see the intention of the model. You see where the model is actually looking. And you have access to the tensors or the vectors here. So you really want full transparency about everything. The goal is that it's the only way to really audit models and be able to know, okay, which one are the outliers and why are they outliers. In this case, it's not looking at what it should be. It should be looking at the baseball diamond, and it's not. So already we know this. So there's a lot of things that we can learn when we explore those reports. And what's really important is to figure out at which stage the model is has too much degradation. And in the real world, there's so many types of transformation, and that's why we build them all and we test them. And it's kind of we're handling pretty lots of data in here. For each point, that means we process the whole data set, score everything, and log it. And when you see for flips, that means that if you flip the image, there's no problem. But if you see like the curve going down here, that means that you will lose all the capabilities of the model the second there's a little bit of change in textures in the image or like the tabular data, depends. So that's the story. We have over 80 transformation. Those are examples, and you can choose from them. And we did this, and we're expanding this to tabular data so that you'll be able to choose, say, from 20 of them and more, so that you can degrade the test set, evaluate them, and know the potential failure. And the good thing with all this is that it can be solved. I mean, I'm pretty dramatic here saying like all models are doomed, but technically you can solve them. You find the weakness, and then you just need to use all these transformation and augment your data set. So your data set will go from, you'll add maybe 200% more data, some with blur, some with noise, and so on. And then you'll be able to make your model robust. So it was dramatic, but the solution is just find where the failures are and then augment your data set. And augmentation, talk to your data scientists. They know there's many techniques. We have some. We also use ours, but there's also so many libraries for this. So in this case, that's kind of an example. No augmentation. Still, I'm staying with snow because I'm from Canada. But then, so you see the degradation was there, but then we augmented that data set, we put images with snow in it, and then it starts performing correctly. So we figure out your operational envelope, what kind of condition you'll deploy your model in. So is it in a factory? So when you have manufacturing, you deploy in a factory, there'll be noise, vibration, and so on. There'll be people walking by, banging the camera. So if the angle of the camera changes, what should you do? So you need to test for all these, and not only this, but that you can compose them. It could be like the lighting will change and also there'll be dust. So you need to also create those reports for a combination of those. And it's kind of, you can have 3, 4, 5 that you can stack together based on the environment. So that's something. And also the good news is that it doesn't only improve the model robustness, but it makes your model will generalize more easily. And you will gain general accuracy. So the number I talked about that everyone really likes, it's also going up because you're making your model more general. It's less sensitive to noise. It's less sensitive to color changes. So that makes, so these are industrial use case we did. So we went from 98 to 99, 67 to 70, 74, just by learning what are the failures and how to augment it. And different client use case. I mean, we did predictive maintenance, tabular data, and so on, and it's always, we use our tools to do those things, and we also offer tools for people to use them online. And maybe I want to share a few things, whether you use those tools or don't. Make sure that you have access to all the data as much as you can. Even if you build it in-house, just access it. Focus from day one on safety and robustness, and engage the stakeholders right away. Don't wait so put everyone in the same room, tell them about the solution, and then make sure that it's an iterative development. And these principles, I think, that's what we've been using, and so that's kind of what we integrate in our software, so that we make sure that we get the benefits such as enhanced collaboration, accelerate model development, and instead of months of you train the model, then people get involved, why doesn't it work, you deployed it and it doesn't work. So then you know just in a few days you can make your model achieve better performance. And also because you brought them in, the stakeholders from day one, that goes from the CEO to the people in charge of operations, and then you have the buy-in right away. And if people can see it, then they will believe it and be able to, as domain expert, give their input into how to improve the model. And and if you understand the operational envelope, you will reduce risk and not have dramatic failures. So that's pretty much it. And you can come see us at the booth if you want to talk more, or you can also get me on LinkedIn. So that's it.
A really insightful presentation. We have some time for questions, so would like to go first? The mic is coming.
Hi, so do you only do image data, so computer vision, or also other kind of machine learning?
Yeah, we do also tabular data. So we're developing this at the moment. We started with computer vision because it's easy to explain, and there's an educational process that we need also to go through, because testing and evaluation is just kind of really appearing now in machine learning. Like the reality came in, and like you need to test and evaluate. So visually, my message goes better this way. So now we started like a couple months ago, tabular data. We'll go to NLP and so on. And in this case, we also support things that are not deep learning. It's also possible. So yeah.
Hi. Hi. For your talk, thank you very much. I had a question about, like, it's very useful to detect what kind of data you still need to improve your model. But one of the biggest problems with data augmentation is that sometimes it's not feasible computationally to scale up your data set to like 200%, right?
Yeah.
Is there also a way to detect what kind of data doesn't necessarily improve your model?
Yeah, through the iterative process, you augment your data with a certain type, and you'll see it. Sometimes blur will improve, like all the motion blurs, it will improve the colors, so they kind of reinforce each other. Sometimes if you become robust to noise, you'll see other robustness, so all the curve will go up. And some of them are, they're not that separate, you know, so if you improve one, some of them will follow, so they're bound together. So as long as you kind of do an iterative process, you'll be able to achieve it. And what I found is that the models have a lot of capacity that is unused to make them robust. So let's say maybe if you augment your data, multiply by 2, it's still feasible, you can still train, and there won't be too much competition within the data set. So as long as your annotation are well done, so yeah.
Thank you.
Final question?
Hi.
For a very nice presentation. Closer to the mic. Okay, that's better. I was wondering, are there any standards being developed, for instance, in relation to safety? How do you know when a particular system is or AI model is safe to use in an industrial environment?
Yeah, I would say it's taking time. Even the IEEE standards is moving along. There's committees. People will be talking for a long time, and all these documents are coming out. And when I read them, they're very general, like almost like philosophical. So we just thought, like, okay, let's just build something that will help us with our clients and my team, and offer these for other people to use. And so we're kind of building this, and we're also working with a lot of those organizations to kind of establish those standards. So yeah, so it's a kind of a process. Everyone's kind of climbing the ladder of safety. Yeah.
So thank you so much, Patrick.
All right, thank you. Bye-bye.